All right, so you're given a rectangular coordinate triple integral, and the question is to convert it to cylindrical and spherical coordinate system. How do you solve this? Well, first, remember that it's surface to surface, curve to curve, and point to point, and that means you have to figure out what this is, and then you have to think about building this. Okay. So let's first figure out what these are. First, because you have dy here, this should be thought as y equals to negative square root of 9 minus x squared. If you square both sides, that's y squared equals to actually negative squares to positive, so you just end up with 9 minus x squared. If you move the x squared to the other side, you get x squared plus y squared equal to 9. What is this?
Circle.
It's a circle of radius 3. However, it's not the full circle. If you just have this, it's not the full circle because y can only take negative values. What does that mean?
It's a bottom.
It's the bottom half because y coordinate is always negative. So this will just represent this part. So this should be really thought as the bottom circle to y equal to 0. What's y equal to 0? This one, right? So you're starting here and you're ending there. That's the way you're going. However, your x is from 0 to 3. What does that mean?
It's moved up. It's only
You're only working with x between 0 to 3, so you're only working with this part. So that's what this is. This should be thought as this domain here. And over this region, you're going from surface to surface. So let's think about now what that is. This thing here is z equals to negative square root of 9 minus x squared minus y squared. And again, if you square both sides, you get z squared equal to 9 minus x squared minus y squared. And moving everything to the other side, you get x squared plus y squared plus z squared equal to 9. And if you take the xy trace, yz trace, and xz trace of this, you get circles in all three, which means this must be a sphere of radius 3. So this is actually a sphere of radius 3. And then going back, what will this give you then? It will be the bottom half sphere. Okay? So you're going to get a bottom half sphere, and this one will be the top half sphere. Okay? So here's what's happened. If you just had these two surfaces, it's like you have this coordinate system, and on this coordinate system you have this circle, and then over it you have this sphere of radius 3. But we're not getting the entire sphere because we're limiting ourselves to surfaces over this region here, this region. Now, what is this region on this picture? Well, that's the region where y is negative. You're going in the negative direction for y, but x direction is positive, right? So if I say this is x and that's y and that's z, it's a negative for the y and positive for x, so it must be this one. Right there, okay? And we're trying to go from the bottom surface to the top sphere, top surface, right? Bottom to the top. And if you go there, passing through this red region here, then you're going to end up with the following thing, which is like this one to there, okay, with this. So it's actually it's like this. Okay. So if you had an orange and you chopped it once and twice, so you get four pieces of orange. This is like one of them. That's what you're getting. So that's the domain of integration. Right? Yes.
So it's negative z to positive z?
It's the negative surface to the positive surface over this quarter circle, over this thing. The surface to surface, curve to curve, and point to point. See, once you do this integration, that has the effect of doing this, right? So you get the flattened object, which is this disk right here. And then once you integrate this with respect to y, that has the effect of flattening it. So you end up with this interval from 0 to 3. That's what's happening. All right, now let's try to represent this in terms of polar coordinates. Now for polar coordinates, you have to involve dz, dy, rd, rd theta, right? Rd, rd theta. That's what you use for polar. Now what is x in terms of polar? R cosine theta. R cosine theta. And what about z? Z is z. And in cylindrical coordinates, z doesn't change. Only x and y are changed to r and theta. So that's what you're trying to integrate. Now we have to figure out what to put for the bounds. So for the surface, we have to somehow come up with the representation of this surface and that surface. Okay. So I have to figure out how to rewrite this in terms of r and theta. But if you recall, what is r squared in terms of x and y?
R.
No, r is square root of x squared plus y squared, right? So r squared is x squared plus y squared. And therefore, if I have 9 minus x squared minus y squared, that's like 9 minus r squared. And therefore, this can be written as negative square root of 9 minus r squared, and the top one will be square root of 9 minus r squared. So that's what we write. Negative square root of 9 minus r squared, square root of 9 minus r squared. These are the way that the surfaces are written. It's still z equal to the bottom surface, z equals to the top surface, bottom surface to the top, but now you're using r squared rather than x squared and y squared because we are in the cylindrical coordinates. In the cylindrical coordinates, you can't use x and y. Okay? That's what we have. And then, what about the r? So once you integrate it, now you have to fill these in. You just have to describe this one. Okay. So r goes from where to where for this? If you have any ray, it starts from 0 until where? 3. So 0 to 3. And what about the angle? Starts from here to there. Right? Negative pi over 2 until 0. Okay. Either this, or you can also use 3 pi over 2 to 2 pi. So there's more than one way to do it. So this is one possible answer, or you could also do 3 pi over 2 to 2 pi. Okay. All right. So that's what you do for cylindrical. And if you notice, all we had to do for these was to just rewrite that equation in terms of r and theta. And that was because since we have dz here and dz there, since that didn't change, when we described the surfaces, all we had to do was to come up with a different description of the same surface. Okay? Now, it turns out that when you try to do this for spherical, it's no longer true. You actually have to start from the scratch. So let's try to do this in spherical coordinate system. In spherical coordinate system, r is rho sine phi. That's the formula. And then z is rho cosine phi. So that's what we use. And then instead of r dz dr theta, we have rho squared sine phi as the formula, d rho d theta d phi. And actually for spherical coordinate system, although we are starting from scratch, this is the only hard part. Trying to figure these out, this is easy. Because first, rho. What should rho be? If you start from the origin and you shoot a laser, it always starts from 0 and it has overlap with the domain until where? 3. Because this sphere has radius 3, it's from 0 to 3. Now what about the theta? Well, theta is same as this theta here, right? So whatever you used for theta before for the cylindrical, you can reuse for the theta here. So it's negative pi over 2 to 0. How about phi? You start from, the highest point is here at the North Pole. You go down to the South Pole, right? So what's phi? No, phi is the angle. So what's the angle from the North Pole if you're at the North Pole?
0.
0. What's the the angle from the North Pole if you're at the South Pole?
Pi.
Pi, 180 degrees, right? So you start from 0, you end up with 180 degrees. So it's from 0 to pi. And this is same as this and same as this. So if you computed each individual ones in some way, actually this is the hardest to do. This will be the easiest to calculate, right? But if you do the calculation in any form, at the end of the day, you'll find out that they all give you the same answer. Okay? That's it.